Imagine everything you've ever known. Every person, every planet, every star in the sky, compressed into a space smaller than a grain of sand. Now, imagine that sand grain exploding into everything that exists. This isn't science fiction. This is our reality. This is our origin story. Take a breath. That oxygen you just inhaled was forged in the heart of a dying star billions of years ago. The iron in your blood? Created in a massive cosmic explosion before Earth even existed. You aren't just observing the universe, you're made of it. But how can we possibly know this? How can we be so bold as to claim we understand the birth of everything? The answer lies in one of humanity's greatest intellectual achievements: our understanding of the universe's origin. Yet this understanding is far from complete. 13.8 billion years ago, from a point infinitely dense and infinitely hot, space, time, and matter erupted into existence. Every galaxy, every star, every planet, and every atom that exists today emerged from that one moment. This is a story so vast, so complex, that it challenges the very limits of human comprehension. But what triggered this cosmic birth? What existed before? And how can we be sure our current understanding is correct? Today we stand at a unique moment in human history. Our technology has advanced enough to test theories that were once purely philosophical. We're probing the very edges of space and time, uncovering clues about our cosmic origins that have been hidden since the dawn of existence. In this video, we'll take you on a journey through time itself. We'll explore the competing theories about our universe's birth, examine the evidence that supports them, and challenge what we think we know about the nature of reality itself. From quantum mechanics to cosmic inflation, from the first seconds of creation to the vast cosmic web we see today, we're about to unravel the greatest origin story ever told. And before we dive into this cosmic mystery, if you're enjoying this content, don't forget to like this video and subscribe to Space Mysteries for more mind-bending explorations of our universe. Join us as we answer the question, what's the real story of the universe's origin? In the 1920s, astronomer Edwin Hubble made a discovery that would shake the foundations of science. Using the 100-inch Hooker telescope at Mount Wilson Observatory, then the world's most powerful, he observed something extraordinary in the Andromeda Nebula. What astronomers had thought was a cloud of gas within our own galaxy was actually an entirely separate galaxy, millions of light years away. This discovery instantly expanded the known size of the universe by orders of magnitude. But Hubble wasn't done. By carefully measuring the light from distant galaxies, he noticed something even more remarkable. These galaxies were moving away from us. More specifically, he found that the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, led to one of the most profound realizations in human history. The universe is expanding. This expansion posed a fascinating question. If the universe is expanding, what happens when we run this cosmic film in reverse? This simple thought experiment led to an extraordinary conclusion. Wind back the clock far enough, and everything in the universe, all the matter, energy, space, and time itself, must have emerged from a single point. This idea was first proposed by Georges Lemaitre, a Belgian priest and physicist, in 1927. Lemaitre suggested that the universe began with what he called the primeval atom, an initial state of infinite density from which everything else emerged. His mathematical models showed how this cosmic explosion could have led to the expanding universe we observe today. Initially, Many scientists, including Einstein himself, were skeptical of this radical idea. Einstein famously told Lemaitre, "Your mathematics is correct, but your physics is abominable." The term Big Bang would come later, ironically coined as a criticism by astronomer Fred Hoyle during a 1949 BBC radio broadcast. Hoyle, who favored a steady-state theory where the universe had always existed, meant the term to be dismissive. Instead, it captured the public imagination and became the accepted name for our universe's birth. The evidence for this extraordinary beginning would continue to mount. In 1948, physicists Ralph Alpher, Hans Bethe, and George Gamow published the famous alpha-beta-gamma paper, named after the first letters of their surnames, which showed how the light elements, hydrogen, helium, and lithium, could have been created in the first few minutes after the Big Bang. Their calculations predicted specific abundances of these elements, which matched what astronomers observed in the universe. But the smoking gun came in 1964, when astronomers Arno Penzias and Robert Wilson were working with a sensitive microwave antenna at Bell Labs in New Jersey. They discovered a persistent background noise that couldn't be eliminated. This cosmic microwave background radiation, as we now know it, is essentially the afterglow of the Big Bang itself, the oldest light in the universe. It's like finding the universe's birth certificate, written in radiation. This radiation had been predicted by Ralph Alpher and Robert Herman in 1948, but finding it was revolutionary. The cosmic microwave background radiation shows us the universe as it was just 380,000 years after the Big Bang, when it had cooled enough for the first atoms to form and light to travel freely through space. This ancient light carries within it the imprint of the early universe's structure, the seeds that would eventually grow into the galaxies and clusters we see today. But understanding the Big Bang theory requires us to grapple with concepts that seem to defy common sense. The early universe wasn't just hot, it was incomprehensibly hot, reaching temperatures of over a trillion degrees in its first moments. It wasn't just dense, it was infinitely dense, containing all the matter and energy of our current universe in a space smaller than an atomic nucleus. The mathematics tells us that at the moment of the Big Bang, the laws of physics as we know them break down completely. Our equations can't describe what happened at the exact moment of creation, because our current physical theories aren't equipped to handle the extreme conditions that existed then. This is known as the singularity problem, and it remains one of the greatest challenges in modern physics. Yet the evidence for the Big Bang theory is overwhelming. Beyond the cosmic microwave background radiation and the abundance of light elements, we can observe the large-scale structure of the universe, the way galaxies are distributed in space. This cosmic web, with its vast filaments and voids, aligns perfectly with what we'd expect from an expanding universe that began in an incredibly hot, dense state. The theory has also made predictions that were later confirmed by observation. For example, it predicted the existence of dark matter, invisible matter that we can only detect through its gravitational effects. While we still don't know exactly what dark matter is, we can see its influence in the way galaxies rotate and clusters move. But perhaps the most mind-bending aspect of the Big Bang theory is what it tells us about the nature of time itself. Many people ask what came before the Big Bang, but this question might not even make sense. According to our best understanding, time itself began at the moment of the Big Bang. Asking what came before is like asking what's north of the North Pole. It's a question that loses its meaning at the boundary. The Big Bang theory also presents us with a remarkable perspective on our own existence. Every atom in your body has a history that stretches back to that initial moment. The carbon in your cells was forged in the hearts of dying stars. The oxygen you breathe was created through stellar nucleosynthesis. The iron in your blood was produced in massive stellar explosions that occurred billions of years ago. We are, quite literally, made of stardust. Understanding this history isn't just an academic exercise. It's fundamental to understanding our place in the cosmos. The Big Bang Theory shows us that we are not separate from the universe. We are an intrinsic part of it, made from the same matter that was present at the beginning of time. Our very existence is a testament to the incredible journey that matter and energy have taken over billions of years. As we move forward in this documentary, we'll delve deeper into the mysteries that remain. We'll explore what might have triggered the Big Bang, examine the fraction of a second after it occurred, and investigate the forces that shaped our universe into what we see today. We'll confront questions that challenge our understanding of reality itself. Is our universe unique? Could there be others? What role does quantum mechanics play in the origin of everything? The importance of these questions extends beyond pure scientific curiosity. Understanding our cosmic origins helps us comprehend our place in the vast cosmic drama. It reminds us that despite our apparent insignificance in the face of such immensity, we're part of something truly extraordinary, a universe that has evolved from simple beginnings to create complexity, consciousness, and the ability to understand its own history. But before we venture into these deeper waters, it's important to appreciate the magnitude of what we've already discovered. In just a century, we've gone from believing the Milky Way was the entire universe to understanding that we live in just one of billions of galaxies, all born from a single cosmic event that occurred 13.8 billion years ago. We've learned to read the cosmic signatures left behind by events that occurred billions of years before Earth existed. We've developed mathematics and physics capable of describing the evolution of the entire observable universe. This is where our journey begins, not with myths or legends, but with evidence, observation, and the remarkable human capacity to uncover the secrets of our cosmic origins. As we proceed, we'll see how each new discovery has brought us closer to understanding not just where we came from, but who we are in the grand cosmic scheme. The story of the universe's origin is our story, and it's far more magnificent than any myth could have imagined. What existed before existence itself? It's a question that pushes the boundaries of human comprehension and challenges our most sophisticated mathematical models. To understand this profound mystery, we must venture into the strange realm where quantum mechanics meets gravity, where time becomes malleable, and where our conventional understanding of before and after breaks down completely. The quantum vacuum, far from being empty nothingness, writhes with activity at the smallest scales. Virtual particles continuously pop in and out of existence in a cosmic dance called quantum fluctuations. These aren't mere theoretical constructs. They manifest in measurable effects like the Casimir force, where two parallel metal plates placed extremely close together experience a tiny attractive force. This force arises because the space between the plates can support fewer virtual particle fluctuations than the space outside, creating a pressure difference that pushes the plates together. It's direct evidence that empty space has physical properties and energy of its own. The quantum vacuum state holds energy, vacuum energy, which has weight and warps space-time itself. This creates one of physics' greatest puzzles, the vacuum catastrophe. Theoretical calculations suggest this energy should be enormous, yet astronomical observations indicate a much smaller value. The difference is staggering, Theoretical predictions exceed observations by 120 orders of magnitude. This vast discrepancy hints at something fundamental we still don't understand about the nature of space itself. Quantum fields permeate all of space, forming the foundation of reality. Everything we consider fundamental, particles, forces, even space-time itself, may be manifestations of these fields. Like an ocean that appears calm on the surface while teeming with activity beneath, quantum fields maintain a constant background of fluctuations even in their lowest energy state. These fluctuations aren't random noise. They're governed by precise mathematical rules that might hold the key to understanding the pre-Big Bang state. The phenomenon of quantum tunneling reveals something profound about reality. In the quantum world, particles can traverse barriers that classical physics deems impossible to cross. This occurs because quantum objects exist in states of probability rather than definite positions. These probabilities can extend beyond seemingly impenetrable barriers, allowing particles to appear on the other side. This same principle might apply to entire universes. Our universe might have quantum tunneled from a previous state, not necessarily a previous time, but a different configuration of reality itself. Eternal inflation theory suggests that the vacuum state of space is inherently unstable. Quantum fluctuations can cause tiny regions of space to begin expanding exponentially, creating separate universes with their own physical laws and constants. This leads to the concept of the multiverse, an infinite cosmic foam eternally spawning new universes through quantum processes. Each universe bubble could have different physical constants, different numbers of dimensions, and different fundamental forces. The mathematical framework of string theory presents another perspective on pre-Big Bang physics. It suggests that the fundamental building blocks of reality are not point-like particles, but tiny vibrating strings in higher dimensional space. Different vibrational patterns of these strings create different particles and forces. The theory requires extra spatial dimensions beyond the three we observe, dimensions that might be curled up at scales too small to detect, or might extend in directions our universe can't access. The holographic principle suggests our three-dimensional reality might be a projection of processes occurring in a lower dimensional space. This isn't mere speculation. It's supported by precise mathematical correspondences between certain quantum field theories and gravitational systems. The AD-S-CFT correspondence provides exact relationships between theories in different dimensions, hinting at a deeper structure underlying reality itself. Quantum entanglement offers another crucial perspective. When particles become entangled, their quantum states are connected regardless of distance, what Einstein called spooky action at a distance. Some theorists propose that space itself might emerge from fundamental quantum entanglement between abstract quantum bits of information. This it from qubit hypothesis suggests space, time, and matter might emerge from pure information processes occurring at a more fundamental level. Loop quantum gravity takes a different approach, suggesting that space itself is quantized, built from discrete units at the Planck scale, about 10 to the minus 35th meters. These units combine to form spin networks, quantum structures that could describe the fundamental nature of space. In this framework, the Big Bang might have been a bounce from a previous phase of the universe. When matter becomes extremely dense, quantum gravitational effects could become repulsive, preventing true singularities and allowing for a cyclic universe. The Wheeler-DeWitt equation attempts to describe the quantum state of the entire universe, including space-time itself. Unlike other physical theories, it doesn't treat time as a fundamental quantity. Instead, it describes a timeless universe where change emerges only at the classical level. This suggests that time might be an emergent phenomenon rather than a fundamental aspect of reality, arising from more basic quantum mechanical processes. The concept of decoherence provides insight into how the classical world we observe emerges from quantum mechanics. As quantum systems interact with their environment, they lose their quantum properties and begin behaving classically. This might explain how our classical universe emerged from a quantum state near the Big Bang. The process might also help explain why we experience time in one direction, despite the time symmetry of fundamental physics. Information plays a crucial role in these theories. According to quantum mechanics, information cannot be truly destroyed, only scrambled. This leads to profound questions about the nature of reality. If information is conserved, what happened to the information from any previous phase of the universe? How does information survive the transition through a quantum bounce or tunnel? These questions connect to the black hole information paradox and suggest deep relationships between information, quantum mechanics, and gravity. Recent developments in quantum cosmology have introduced quantum gravity, the idea that space-time might be more like a network of relationships between quantum events rather than a smooth continuum. In this picture, space and time emerge from more fundamental building blocks, similar to how temperature emerges from the collective behavior of atoms. At high energies, near the Big Bang, these building blocks might arrange themselves in ways that don't correspond to our normal concepts of space and time. The Hartley-Hawking state proposes that the universe had no boundary in the past. Using a mathematical technique called Wick rotation, time becomes imaginary near the Big Bang, smoothing out the initial singularity. In this picture, asking what came before the Big Bang becomes meaningless, like asking what's north of the North Pole. The universe simply is, with time as we know it emerging only as things cool down and spread out. Twistor theory provides a radically different mathematical framework for understanding space-time. Instead of points in space and time, it describes reality in terms of light-like relationships between events. This approach naturally incorporates quantum mechanical principles and might explain how classical space-time emerges from more fundamental structures. The emergence of time itself presents profound philosophical questions. If time emerged from something more fundamental, what does that mean for concepts like causality and free will? Some philosophers argue that our entire conception of reality needs to be revised to accommodate a timeless, fundamental reality. The very notion of before might be inadequate for describing the ultimate nature of existence. These theories suggest that the question, what came before the Big Bang, might be fundamentally misguided. Instead of a simple linear progression of events, we might need to envision reality in terms of quantum superpositions, emergent phenomena, and mathematical structures that transcend our everyday concepts of space and time. The mystery of what existed before the beginning remains one of science's greatest challenges, pushing us to expand not just our knowledge, but our very capacity to comprehend the nature of existence itself. When we talk about the first second of the universe, we're actually discussing an almost incomprehensible span of different epochs, each with its own distinct physics and characterized by energies far beyond anything we can create in our most powerful laboratories. This brief moment contained the seeds of everything we see today, from the largest galaxy clusters to the smallest subatomic particles. The Planck epoch, lasting from time 0 to 10 to the power of -43 seconds, represents the absolute limit of our physics. At this scale, the temperature reached an unfathomable 10 to the power of 32 degrees Kelvin, so hot that the four fundamental forces we know today, Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified into a single superforce. The very concept of space and time as we understand them breaks down at this scale, where quantum effects and gravity become equally important. During this epoch, our universe was smaller than a proton, yet contained all the energy that would eventually become the billions of galaxies we see today. The density was so extreme, 10 to the power of 93 grams per cubic centimeter, that a volume the size of a grain of sand would have contained more mass than our entire observable universe does today. At these scales, space itself wasn't smooth, but had a foam-like structure, with quantum fluctuations creating and destroying microscopic black holes in an instant. As the universe expanded and cooled to 10 to the power of minus 36 seconds, it entered the grand unification epoch. Here, gravity separated from the other forces, but electromagnetism and the nuclear forces remained unified in what physicists call a grand unified theory, GUT, state. The temperature was still an incredible 10 to the power of 28 degrees Kelvin, hot enough that the distinction between matter and energy was meaningless. The universe was filled with a hot soup of quarks, leptons, and their antimatter counterparts, all moving at nearly the speed of light. Then something extraordinary happened. Between 10 to the minus 36 and 10 to the minus 32 seconds, the universe underwent a phase of exponential expansion called cosmic inflation. During this brief moment, space itself expanded faster than the speed of light, growing by a factor of at least 10 to the 78th power. This expansion was so rapid that tiny quantum fluctuations in the early universe were stretched to cosmic scales, seeding the large-scale structure we see today in the distribution of galaxies. Inflation solved several cosmological puzzles. It explains why the universe appears flat and uniform on large scales, and why regions of space that could never have been in causal contact have the same temperature, the so-called horizon problem. But it also predicts that our observable universe is just a tiny fraction of the total universe, with most of it lying forever beyond our cosmic horizon. The end of inflation was marked by a process called reheating, where the energy driving inflation was converted into a hot plasma of particles and radiation. This process wasn't uniform. Quantum fluctuations during inflation led to slight variations in how this energy was distributed, creating the first seeds of cosmic structure. At 10 to the minus 32 seconds, the universe entered the electroweak epoch. The strong nuclear force had separated from the electroweak force, but electromagnetism and the weak nuclear force remained unified. The temperature was now only 10 to the 15th degrees Kelvin. During this epoch, the Higgs field, which gives particles their mass, began to take on its modern form. The universe was still too hot for protons and neutrons to form. Instead, it was filled with a quark-gluon plasma, a state of matter so extreme that we've only recently managed to recreate it in particle accelerators like the Large Hadron Collider. In this plasma, quarks and gluons moved freely, rather than being bound into hadrons, as they are today. At 10 to the minus 12 seconds, the universe cooled enough for the electroweak force to split into the electromagnetic and weak nuclear forces we know today. This symmetry breaking was accompanied by another phase transition, where the Higgs field settled into its current state, giving mass to the W and Z bosons while leaving the photon massless. The period from 10 to the minus 12 to 10 to the minus 6 seconds marked the quark epoch. The universe was still too hot for quarks to combine into protons and neutrons, but cool enough for the four fundamental forces to operate as they do today. This epoch was characterized by a continuous creation and annihilation of quark-antiquark pairs, with a slight excess of matter over antimatter, about 1 part in a billion. This matter-antimatter asymmetry, called baryogenesis, is one of the great mysteries of modern physics. Without it, matter and antimatter would have annihilated completely, leaving behind a universe filled only with radiation. The fact that we exist proves this asymmetry occurred, but explaining its exact mechanism remains a major challenge. At 10 to the -6 seconds, the temperature had dropped to about 10 to the 13 degrees Kelvin, cool enough for quarks to begin combining into protons and neutrons in a process called hadronization. This marked the beginning of the hadron epoch. The quark-gluon plasma condensed into hadrons, much like steam condensing into water droplets, but at temperatures trillions of times hotter. During this epoch, hadrons and antihadrons were constantly being created and destroyed in particle-antiparticle collisions. As the universe continued to cool, it became harder to create new hadron-antihadron pairs, and most existing pairs annihilated each other. Only that tiny excess of matter over antimatter, 1 part in a billion, survived to form the matter we see today. By 10 to the -4 seconds, the temperature had fallen to about 10 to the 12 degrees Kelvin, cool enough that hadron-antihadron pairs could no longer be created in significant numbers. The surviving protons and neutrons began to dominate the energy density of the universe, marking the beginning of the Lepton epoch. During the Lepton epoch, from 10 to the -4 to 1 second, the universe was dominated by leptons, electrons, positrons, neutrinos, and their antiparticles. Like the hadrons before them, these particles were constantly being created and destroyed in particle-antiparticle collisions. The universe was still hot enough that photons could spontaneously convert into electron-positron pairs, and vice versa. Neutrinos played a crucial role during this epoch. Until about 1 second after the Big Bang, neutrinos were in thermal equilibrium with other particles through the weak nuclear force. But as the universe cooled, the rate of neutrino interactions dropped dramatically. At this point, neutrinos decoupled from matter, beginning their journey through space as the cosmic neutrino background, a remnant that still permeates the universe today, though it's even harder to detect than the cosmic microwave background. The first second after the Big Bang wasn't just the beginning of our universe. It was a series of crucial transitions that determined the fundamental characteristics of our cosmos. The slight excess of matter over antimatter, the strength of the fundamental forces, the seeds of cosmic structure, all were established in these earliest moments. The physics of the first second challenges our understanding of nature at the most fundamental level. It requires us to combine quantum mechanics with gravity to understand physics at energies far beyond what we can test in laboratories, and to grapple with conditions so extreme they seem to defy comprehension. Yet the evidence for this sequence of events is written in the very structure of our universe, in its uniformity on large scales, in the abundance of light elements, and in the cosmic microwave background radiation. This fleeting moment set the stage for everything that would follow. The fundamental constants and forces established in the first second would ultimately determine whether stars could form, whether chemistry could exist, and whether life itself would be possible. In many ways, we are all children of this first second, our very existence encoded in the physics of the universe's earliest moments. Every atom in existence tells a story of cosmic creation. The calcium in our bones, the iron in our blood, the carbon in our cells. Each element represents a different movement in an extraordinary symphony that began in the universe's youth. This is the story of how the simplest elements formed into the complex atomic structures that make up everything we see today. In the aftermath of the first second, our universe was an unimaginably hot soup of particles, dominated by radiation. As temperatures dropped below 10 billion degrees Kelvin, the first protons and neutrons began an elaborate dance that would create the earliest atomic nuclei. This process, known as Big Bang nucleosynthesis, marked the beginning of chemical complexity in our universe. The earliest moments of nucleosynthesis were dominated by a delicate balance between nuclear forces and thermal energy. At these extreme temperatures, any atomic nuclei that formed would be immediately torn apart by high-energy photons. But as the universe expanded and cooled, a narrow window of opportunity opened, a period lasting only about 3 minutes that would determine the initial chemical composition of the cosmos. During these crucial minutes, protons and neutrons collided in a precise sequence of nuclear reactions. The first step was the formation of deuterium, an isotope of hydrogen containing 1 proton and 1 neutron. But deuterium faced a significant challenge known as the deuterium bottleneck. Even though protons and neutrons were abundant, the universe was still so hot that photons would immediately break apart any deuterium nuclei that formed. Only when the temperature dropped below 1 billion degrees could deuterium survive long enough to participate in further nuclear reactions. This marked the beginning of a rapid chain of nuclear fusion events. Deuterium nuclei combined to form helium-3 and tritium. These isotopes then fused into helium-4, a particularly stable configuration of 2 protons and 2 neutrons. The efficiency of this process was remarkable. Within minutes, about 25% of the protons and nearly all the neutrons in the universe had been incorporated into helium-4 nuclei. This ratio, roughly 75% hydrogen and 25% helium by mass, represents one of the most important predictions of Big Bang cosmology, and its precise match with observations provides compelling evidence for our understanding of the early universe. The role of neutron decay was crucial during this period. Free neutrons are unstable, with a half-life of about 10 minutes. As the universe cooled, any neutrons that hadn't been incorporated into atomic nuclei began to decay into protons through the weak nuclear force. This process would have converted all neutrons to protons if nucleosynthesis hadn't occurred when it did, leaving a universe composed entirely of hydrogen. Trace amounts of other light elements were also produced during this period. Lithium-7 formed in tiny quantities, about 1 part in 10 billion. Beryllium-7 was created, but later decayed to lithium-7. The abundance of these light elements serves as another crucial test of Big Bang theory, as their predicted quantities closely match what we observe in the oldest stars and gas clouds. The formation of these first elements was profoundly influenced by the presence of dark matter. Though invisible and unable to participate directly in nuclear reactions, dark matter's gravitational effects helped shape the distribution of ordinary matter. Its gravitational pull created the first subtle variations in density that would later grow into the cosmic web of galaxies and clusters we see today. As the universe continued to expand and cool, the era of primordial nucleosynthesis came to an end. The temperature and density had fallen too low for nuclear fusion to continue. The universe entered a period dominated by radiation, where matter existed primarily as a plasma of ionized hydrogen and helium, along with free electrons. This plasma state was crucial for the development of the cosmic microwave background radiation. Photons couldn't travel far without encountering free electrons, keeping matter and radiation in thermal equilibrium. The universe was effectively opaque, like a dense fog where light constantly scattered off free electrons. The next major transition occurred around 380,000 years after the Big Bang, when the temperature dropped to about 3,000 degrees Kelvin. At this point, Electrons could finally combine with nuclei to form stable atoms, a process known as recombination. This marked the emergence of the first true atoms of hydrogen and helium. The process of recombination had profound consequences. As electrons combined with nuclei, photons could suddenly travel freely through space without constantly scattering off free electrons. This released the cosmic microwave background radiation, ancient light that still permeates the universe today, carrying information about the conditions when the first atoms formed. The chemistry of this early universe was remarkably simple compared to what we know today. With only hydrogen and helium, plus trace amounts of lithium, complex chemical reactions were impossible. The formation of heavier elements would have to wait for the first stars to form, hundreds of millions of years later. In the darkness that followed recombination, gravity slowly began to concentrate matter into denser regions. The interaction between ordinary matter and dark matter played a crucial role in this process. Dark matter, unaffected by radiation pressure, had already begun forming gravitational wells. Ordinary matter gradually fell into these wells, setting the stage for the formation of the first stars. The distribution of elements during this period wasn't uniform. Quantum fluctuations from the universe's earliest moments had been stretched by cosmic inflation, creating slight variations in density. These variations were preserved in the distribution of hydrogen and helium, creating patterns that would influence where the first stars and galaxies would form. The cosmic web began to take shape during this era. Regions slightly richer in matter grew increasingly dense, while less dense regions became more empty. This process was guided by the gravitational effects of dark matter, which made up about 85% of all matter in the universe. The complex interplay between dark matter, ordinary matter, and radiation pressure created the intricate filamentary structure we observe in the universe today. Temperature differences played a crucial role in this process. In denser regions, atoms could cool more efficiently through collisions, allowing matter to concentrate further. This created a feedback loop. Denser regions became even denser, while less dense regions became more empty. These temperature variations are preserved in the cosmic microwave background radiation, providing a snapshot of conditions when the first atoms formed. The formation of molecular hydrogen marked another crucial step in chemical evolution. Under the right conditions, two hydrogen atoms could combine to form H2 molecules. Though rare in the early universe, these molecules were crucial for the formation of the first stars, as they could cool gas clouds more efficiently than atomic hydrogen alone. The abundance patterns established during this period left a lasting imprint on cosmic chemistry. The ratio of hydrogen to helium determined how efficiently the first stars could form and what elements they would produce through nuclear fusion. The slight excess of matter over antimatter established much earlier ensured there was matter available to form atoms in the first place. The role of neutrinos during this period is particularly intriguing. Though they had decoupled from matter much earlier, their gravitational effects influenced how matter clustered on large scales. The cosmic neutrino background, though impossible to detect directly with current technology, continues to influence cosmic structure to this day. The pristine nature of the early universe's chemistry allows us to test our theories of cosmic evolution. By studying the oldest stars and gas clouds, we can measure element abundances that haven't changed since these earliest times. These observations provide crucial tests of Big Bang nucleosynthesis and our understanding of early cosmic history. The legacy of this period surrounds us today. The hydrogen fusion that powers our sun, the helium that fills party balloons, the trace amounts of lithium in modern batteries, all have their origins in the first few minutes of cosmic history. The relative abundances of these elements determine the nature of the first stars, the formation of galaxies, and ultimately, the conditions necessary for life itself. This era marked the transition from a universe dominated by radiation to one where atoms could exist stably. It set the stage for all the chemical complexity that would follow, from the nuclear fusion in stars to the biochemical reactions that make life possible. The Symphony of Elements that began in these ancient times continues to play today, its music written in the atomic structure of everything we see around us. The story of cosmic chemistry is far from over. Modern observations continue to reveal new details about how elements formed and were distributed throughout the universe. As we study ancient stars and distant galaxies, we refine our understanding of this crucial period in cosmic history, when the foundations of chemical complexity were first established in our evolving universe. The universe's grandest structures began as mere ripples in the cosmic ocean. From quantum fluctuations stretched by cosmic inflation emerged the vast cosmic web we see today, a network of galaxy clusters, filaments, and voids that form the largest known structures in existence. This is the story of how gravity, working across billions of years, transformed the simple early universe into the rich cosmic architecture we observe today. At first glance, galaxies in the night sky might appear randomly distributed. But zoom out far enough, and a remarkable pattern emerges. Galaxies cluster together like pearls on an invisible string, forming vast filaments that stretch for hundreds of millions of light years. Between these filaments lie enormous cosmic voids, regions of space nearly devoid of galaxies that span tens of millions of light years across. This cosmic web didn't appear fully formed. Its evolution began with tiny quantum fluctuations in the density of matter during the universe's earliest moments. These microscopic variations were dramatically amplified by cosmic inflation, stretching them to macroscopic scales. When inflation ended, these density variations were frozen into the fabric of space itself, becoming the seeds from which all cosmic structure would grow. The key to understanding this evolution lies in the interplay between gravity and expansion. In regions where matter density was slightly higher than average, gravity worked to pull more matter inward. Conversely, regions with lower density gradually emptied out as matter was drawn away by the gravitational pull of denser regions. This process, known as gravitational instability, amplified the initial tiny variations into the dramatic contrasts we see today. Dark matter played a crucial role in this cosmic construction project. Making up about 85% of all matter in the universe, dark matter feels only the force of gravity. It began clumping together long before ordinary matter could, creating a gravitational scaffold around which the visible universe would eventually form. The dark matter formed a complex network of filaments and nodes, creating the basic framework of the cosmic web. As the universe cooled and expanded, ordinary matter gradually fell into these dark matter structures. In regions where dark matter had created deep gravitational wells, gas began to accumulate. As this gas became denser, it could cool more efficiently through collisions and radiation, allowing it to collapse further. This process created the first distinct clouds of gas that would eventually form stars and galaxies. The first stars appeared in the densest regions, where gas had accumulated enough to trigger nuclear fusion. These population 3 stars, as astronomers call them, were unlike any stars we see today. Formed from pristine gas containing only hydrogen and helium, they were incredibly massive, perhaps hundreds of times more massive than our Sun. They lived fast and died young, their brief lives lasting only a few million years. When these first stars exploded as supernovae, they enriched their surroundings with heavy elements forged in their cores. This began a cycle of stellar birth, death, and rebirth that continues to this day. Each generation of stars produced more heavy elements, gradually enriching the cosmos with the chemical building blocks necessary for planets and life. The formation of galaxies marked another crucial step in cosmic evolution. In regions where many stars had formed, their combined gravitational pull attracted more gas and stars. Dark matter halos played a crucial role, providing the gravitational foundation around which galaxies could grow. The largest dark matter halos attracted the most material, leading to the formation of massive galaxies. But galaxies didn't form in isolation. The filamentary structure of the dark matter web created natural pathways along which gas could flow. Where these filaments intersected, particularly massive accumulations of matter could form. These intersections became the sites of galaxy clusters, the largest gravitationally bound structures in the universe. The process of galaxy formation was far from peaceful. As galaxies grew, they frequently collided and merged with their neighbors. These cosmic collisions triggered bursts of star formation and reshaped the participating galaxies. The evidence of these ancient mergers can still be seen today in the disturbed shapes of many galaxies and the streams of stars torn from their original homes. The role of supermassive black holes in this cosmic architecture cannot be overstated. Nearly every large galaxy harbors one at its center, and these cosmic behemoths have profoundly influenced galactic evolution. As they consumed surrounding material, they released enormous amounts of energy, heating nearby gas and regulating star formation. This feedback process helped determine the final sizes and shapes of galaxies. The cosmic web itself continues to evolve. Gravity pulls galaxies along the filaments toward dense clusters, while voids become increasingly empty. This ongoing flow of matter creates a cosmic traffic pattern visible in the motion of galaxies. By mapping these movements, astronomers can trace the distribution of dark matter and understand how the cosmic web formed. The largest structures in the cosmic web, known as superclusters, span hundreds of millions of light-years. Our own Milky Way is part of the local group of galaxies, which in turn is part of the Virgo supercluster. These massive structures represent the culmination of billions of years of gravitational evolution, the final result of those initial quantum fluctuations, stretched by cosmic inflation. Within this grand framework, smaller-scale structures display their own complexity. Individual galaxies show a wide variety of forms: spirals with elegant arms, elliptical galaxies resembling cosmic footballs, and irregular galaxies with chaotic shapes. These different forms reflect different formation histories and the influence of environment on galactic evolution. The distribution of matter within galaxies follows distinct patterns. In spiral galaxies like our Milky Way, most stars orbit in a thin disk, while a spherical halo of dark matter extends far beyond the visible galaxy. The spiral arms themselves are not fixed structures, but rather density waves that move through the galactic disk, triggering star formation as they pass. The space between galaxies, far from being empty, contains the intergalactic medium, a tenuous gas that connects members of the cosmic web. This gas, primarily hydrogen and helium with traces of heavier elements, records the history of cosmic chemical evolution. By studying its composition, astronomers can trace how elements have been distributed throughout the universe. The largest galaxy clusters serve as cosmic laboratories where we can study the interplay of dark matter, ordinary matter, and energy. The hot gas that fills these clusters emits X-rays, revealing the dynamics of matter on the largest scales. Gravitational lensing, the bending of light by massive objects, allows us to map the distribution of dark matter in these cosmic giants. Time plays a crucial role in this cosmic architecture. Because light travels at a finite speed, looking at distant objects means seeing them as they appeared in the past. This allows astronomers to directly observe how cosmic structure has evolved. The most distant galaxies we can see appear as they were billions of years ago, providing snapshots of the universe's youth. The future evolution of cosmic structure is influenced by dark energy, a mysterious force causing the universe's expansion to accelerate. This acceleration works against gravity's tendency to draw matter together, affecting how structures will evolve in the future. Eventually, the expansion may become so rapid that it will prevent the formation of new large-scale structures. Modern surveys have revealed the cosmic web in unprecedented detail. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, creating three-dimensional maps of cosmic structure. These maps reveal a universe organized on the grandest scales, with patterns that emerged from the simplest of beginnings through the inexorable action of gravity across cosmic time. This cosmic architecture represents the universe's shift from simplicity to complexity, from quantum fluctuations to galaxy clusters, from pristine hydrogen gas to complex chemical elements. The story of cosmic structure is one of increasing organization and complexity. It's a testament to how fundamental physical laws, working over vast spans of time, can create the rich cosmic environment we observe today. The study of these structures continues to yield surprises. Astronomers regularly discover new features of the cosmic web, from massive galaxy clusters hidden behind clouds of dust to enormous voids that seem to defy our understanding of structure formation. Each discovery adds another piece to the puzzle of how our universe transformed from its simple beginnings to the complex cosmos we see today. Our journey through cosmic history has followed the standard model of the Big Bang, but it's not the only possible explanation for our universe's existence. Throughout the history of cosmology, scientists have proposed numerous alternative theories, some building upon the Big Bang framework, others challenging it entirely. These alternative models don't just represent scientific curiosity, they embody our attempt to grapple with the deepest questions about existence itself. The steady-state theory, first proposed by Fred Hoyle, Hermann Bondi, and Thomas Gold in 1948, suggests that the universe has always existed and will continue to exist forever in roughly the same form. To account for the observed expansion of the universe, the theory proposes that new matter is continuously created in the spaces between galaxies. This continuous creation would maintain a constant average density throughout space and time. While the discovery of the cosmic microwave background radiation dealt a severe blow to the classical steady-state theory, modified versions have emerged. The quasi-steady-state model, developed by Fred Hoyle and others in the 1990s, proposes that the universe goes through cycles of expansion and contraction, with matter creation occurring in mini-creation events rather than continuously. The oscillating universe theory suggests our universe undergoes endless cycles of big bangs and big crunches. In this model, the current expansion will eventually reverse, leading to a cosmic collapse where all matter and energy compress into a singularity, only to bounce back in a new Big Bang. Each cycle might have different physical constants and laws, making our observable universe just one iteration in an eternal cosmic dance. String theory, while not strictly an alternative to the Big Bang, provides a radically different framework for understanding cosmic origins. It suggests our universe might be a four-dimensional brain floating in a higher dimensional space. In this picture, the Big Bang might have been caused by a collision between our brain and another one, releasing the energy that formed our observable universe. The ekpyrotic universe model, inspired by string theory, proposes that our universe began when two three-dimensional brains collided in a higher dimensional space. This collision would have released enormous energy, creating matter and radiation, while naturally producing the homogeneity and flatness we observe today. Unlike the inflationary model, which requires a period of exponential expansion, the ekpyrotic scenario achieves similar results through the dynamics of brain collisions. Conformal cyclic cosmology, proposed by Roger Penrose, suggests that what we perceive as the Big Bang was actually the end of a previous universe's expansion. As each universe expands eternally, all matter eventually decays into radiation. At this point, with no massive particles left to set a scale, the universe becomes effectively identical to the extremely hot, dense state we associate with the Big Bang, beginning the cycle anew. The holographic universe theory proposes that our three-dimensional reality is actually a projection of information stored on a two-dimensional surface, similar to how a hologram creates the illusion of three dimensions. This isn't merely philosophical speculation. It's supported by precise mathematical correspondences between gravitational theories and quantum field theories in lower dimensions. Quantum loop cosmology, derived from loop quantum gravity, suggests that the Big Bang singularity is replaced by a big bounce. As matter becomes extremely dense, quantum gravitational effects become repulsive, preventing the formation of a true singularity. This would mean our universe emerged from the collapse of a previous universe, with the bounce occurring when quantum effects overcame classical gravitational attraction. The multiverse hypothesis comes in several varieties. The many worlds interpretation of quantum mechanics suggests that every possible outcome of every quantum event occurs in a branching series of parallel universes. The inflationary multiverse proposes that our universe is one bubble in an eternally inflating space, with new universes constantly forming in regions where inflation continues. The fecund universe theory suggests that black holes might give birth to new universes. Each black hole could contain a region of space that expands into a new universe, with slightly different physical constants than its parent universe. This would create a kind of cosmic natural selection, where universes that produce more black holes are more likely to have offspring. Some theories question whether time itself is fundamental. The block universe theory, supported by special relativity, suggests that past, present, and future exist simultaneously in a four-dimensional block of space-time. In this view, the flow of time is an illusion, and the Big Bang is simply one boundary of this four-dimensional structure. The cellular automaton interpretation proposes that the universe operates like a vast computer, with space divided into discrete cells that evolve according to simple rules. This view suggests that quantum mechanics and relativity might emerge from more fundamental digital processes, similar to how complex patterns emerge from simple rules in Conway's Game of Life. The varying speed of light theory suggests that the speed of light might have been much higher in the early universe. This could solve some cosmological puzzles without requiring inflation, as a faster speed of light would allow distant regions of space to have been in causal contact early in cosmic history. Emergence theories propose that space, time, and even physical laws might not be fundamental, but rather emerge from more basic principles, similar to how temperature emerges from the collective behavior of atoms. This approach suggests we might need to rethink our most basic assumptions about the nature of reality. The modified gravity theories propose that our understanding of gravity needs revision. MOND, or modified Newtonian dynamics, suggests that gravity behaves differently at very large scales, potentially eliminating the need for dark matter. While these theories face challenges explaining all observations, they remind us that even our most basic physical theories might need revision. Some theories propose that consciousness plays a fundamental role in the universe. The participatory anthropic principle suggests that conscious observers are necessary for the universe to exist, while others propose that consciousness might be intrinsic to matter at a fundamental level. While highly speculative, these ideas challenge our assumptions about the relationship between mind and reality. The information universe hypothesis suggests that information, rather than matter or energy, might be the most fundamental aspect of reality. In this view, physical laws are expressions of how information can be processed, and the universe itself might be understood as a vast information processing system. Fractal universe models propose that the cosmos exhibits self-similarity across different scales, with patterns repeating from the quantum to the cosmic level. While not strictly an alternative to the Big Bang, these models suggest underlying mathematical principles that might govern cosmic structure at all scales. The plasma universe theory suggests that electromagnetic forces, rather than gravity, dominate cosmic structure formation. While this view struggles to explain many observations, it highlights the importance of considering all fundamental forces in cosmological models. Each of these alternative theories faces challenges. Some make predictions that conflict with observations, while others remain purely mathematical constructs without clear ways to test them empirically. Yet they serve a crucial role in cosmology, challenging our assumptions and forcing us to examine the evidence for our standard models more carefully. The existence of these alternatives reminds us that our current understanding, however well supported by evidence, might not be complete. The history of science shows that seemingly settled questions can be reopened by new evidence or theoretical insights. Even theories that prove incorrect can lead to valuable insights and mathematical tools. These alternative cosmologies also highlight the philosophical questions underlying our study of the universe. What constitutes a valid scientific theory? How do we balance mathematical elegance against observational evidence? What role should philosophical considerations play in evaluating cosmic models? Many of these theories share common themes: the relationship between discrete and continuous phenomena, the role of information in physical law, the possibility of cycles or repetition in cosmic evolution. These recurring ideas might point toward deeper truths about the nature of reality, even if the specific theories prove incorrect. The future might reveal that some combination of these ideas, perhaps along with concepts we haven't yet imagined, provides a more complete picture of cosmic origins. As we gather more data and develop new mathematical tools, we continue to explore these alternatives, guided by evidence but open to revolutionary new ideas about the nature of our universe. In science, extraordinary claims require extraordinary evidence. The story of our universe's origin might seem like the most extraordinary claim of all, but it rests on a foundation of careful observations, precise measurements, and testable predictions. Let's examine the chain of evidence that supports our understanding of cosmic history. The cornerstone of modern cosmology is the observed expansion of the universe. Edwin Hubble's discovery that distant galaxies are moving away from us at speeds proportional to their distance marked the beginning of observational cosmology. This relationship, known as Hubble's law, provides the first crucial piece of evidence for an expanding universe. Modern measurements have refined Hubble's initial observations to extraordinary precision. The Hubble Space Telescope's key project spent years calibrating the cosmic distance ladder, establishing precise distances to galaxies using multiple independent methods. These measurements confirmed the universe's expansion rate to within a few percent, though tension remains between different measurement techniques. Type Ia supernovae serve as standard candles for measuring cosmic distances. These stellar explosions occur when white dwarf stars reach a critical mass, producing remarkably consistent peak brightness. By comparing their apparent brightness with their known intrinsic luminosity, astronomers can measure distances across billions of light-years. These measurements led to the shocking discovery that the universe's expansion is accelerating, revealing the presence of dark energy. The cosmic microwave background radiation provides our clearest window into the early universe. This ancient light, released when the universe became transparent 380,000 years after the Big Bang, carries detailed information about cosmic conditions. The precision map of temperature variations in this radiation, created by satellites like COBE, WMAP, and Planck, reveals the seeds of all cosmic structure. These temperature variations, only about 1 part in 100,000, match exactly what we'd expect from quantum fluctuations amplified by cosmic inflation. The pattern of hot and cold spots provides crucial information about the universe's geometry, composition, and early history. The angular size of these fluctuations indicates that space is remarkably flat, requiring either cosmic inflation or an extraordinary coincidence. The abundance of light elements in the universe provides independent confirmation of Big Bang theory. The predicted ratios of hydrogen, helium, and lithium isotopes created during primordial nucleosynthesis match observations with remarkable precision. This agreement spans 9 orders of magnitude in abundance, from common hydrogen to rare lithium-7. Astronomical spectroscopy reveals these primordial abundances in ancient gas clouds and stars. By studying light from the most distant quasars, we can measure how the chemical composition of the universe has evolved over billions of years. These observations show a clear progression from the simple chemistry of the early universe to the complex elements created by generations of stars. Large-scale structure in the universe provides another line of evidence. Galaxy surveys have mapped hundreds of thousands of galaxies, revealing a cosmic web of filaments and voids. The statistical properties of this distribution, the size of voids, the clustering of galaxies, the evolution of structure over time, match predictions from models based on cosmic inflation and dark matter. The Baryon acoustic oscillation, BAO signal, first detected in 2005, preserves a literal snapshot of sound waves in the early universe. These pressure waves, frozen into the distribution of galaxies when the universe became transparent, provide a standard ruler for cosmic distances. The observed scale of these oscillations confirms our models of cosmic evolution and the role of dark matter. Gravitational lensing reveals the distribution of mass in the universe, including invisible dark matter. When light from distant galaxies passes through massive galaxy clusters, it bends in ways that can only be explained by the presence of far more matter than we can see. These observations provide direct evidence for dark matter's role in cosmic structure. Formation. The polarization of the cosmic microwave background radiation carries additional information about early cosmic history. The pattern of polarization, particularly the B-mode signal, could provide direct evidence of gravitational waves from the inflationary period. While this signal remains elusive, upper limits on its strength help constrain models of cosmic inflation. The distribution of galaxy clusters across cosmic time tracks how structure grows in the universe. X-ray observations reveal huge reservoirs of hot gas in these clusters, while gravitational lensing maps their dark matter content. The abundance and properties of clusters at different distances provide crucial tests of cosmological models. Weak gravitational lensing, the subtle distortion of galaxy shapes by intervening matter, allows astronomers to map dark matter on cosmic scales. Large surveys have revealed the cosmic web of dark matter, showing how it provides the scaffolding for visible structure. These maps match theoretical predictions for how dark matter should cluster under gravity. The cosmic gamma-ray background provides information about energetic processes throughout cosmic history. This high-energy radiation includes contributions from active galaxies, explosive events, and possibly dark matter annihilation. Its spectrum and spatial distribution offer clues about the universe's most energetic phenomena. Neutrino detectors have measured the flux of solar and atmospheric neutrinos, confirming our understanding of nuclear processes in stars. The detection of neutrinos from supernova 1987A provided direct evidence of stellar core collapse. Future detectors might even detect the cosmic neutrino background, providing another window into the early universe. Gravitational wave observatories have opened an entirely new way to study the cosmos. The detection of binary black hole mergers confirms predictions of general relativity and provides new tests of gravity in extreme conditions. Future space-based detectors might detect gravitational waves from the early universe itself. The distribution of primordial magnetic fields offers clues about conditions in the very early universe. These fields, detected through their effects on cosmic ray propagation and radio emission, require explanation in any complete theory of cosmic origins. Their strength and coherence length provide constraints on models of the early universe. High-precision atomic clocks allow direct measurements of fundamental constants and their possible variation over time. These measurements constrain theories that predict changing physical constants and provide tests of Einstein's equivalence principle, a cornerstone of general relativity. Laboratory experiments complement astronomical observations. Particle accelerators probe conditions similar to the early universe, while quantum optics experiments test fundamental aspects of quantum mechanics. These experiments help validate the physics we use to understand cosmic history. The isotopic composition of ancient meteorites provides information about conditions in the early solar system and, by extension, the galactic environment in which it formed. These cosmic time capsules preserve evidence of extinct radioactive isotopes and early solar system processes. The detection of complex organic molecules in interstellar space traces the chemical evolution of the cosmos. These observations show how the building blocks of life could have formed and been distributed throughout the universe, connecting cosmic evolution to the origin of life itself. Ultra-high-energy cosmic rays probe the most energetic processes in the universe. Their energy spectrum and arrival directions provide information about their sources and the magnetic fields they traverse, offering insights into extreme cosmic environments. The precise measurement of cosmic distances using multiple independent methods provides crucial cross-checks of our cosmological framework. From parallax measurements of nearby stars to standard candles and standard rulers at cosmic distances, these measurements build a consistent picture of cosmic scale and evolution. Computer simulations test our understanding by evolving model universes from early times to the present. When these simulations reproduce observed structures and distributions, they validate our physical models. When they fail, they point to gaps in our understanding. The consistency of evidence across multiple, independent lines of investigation provides powerful support for our cosmic model. Each observation adds another piece to the puzzle, creating a coherent picture of cosmic evolution from the earliest moments to the present day. New technologies continue to expand our observational capabilities. 30-meter class telescopes under construction will peer deeper into cosmic history. Next-generation space telescopes will provide unprecedented views of the early universe. Advanced gravitational wave detectors might detect echoes of cosmic birth. This accumulation of evidence doesn't mean we understand everything. tensions between different measurements of cosmic expansion, unexplained features in cosmic ray spectra, and other anomalies remind us that surprises likely await discovery. Science advances by investigating these discrepancies, pushing the boundaries of our understanding ever further. Despite all we've learned about our cosmic origins, profound mysteries remain. Like a detective story where each answer reveals new questions, our growing understanding of the universe has uncovered deeper enigmas that challenge our most fundamental theories. The quest to understand our origins continues to drive us toward new frontiers of knowledge and human understanding. Dark energy, perhaps the greatest cosmic mystery, continues to defy explanation. This invisible force driving the accelerating expansion of our universe appears to be woven into the fabric of space itself. Yet its observed strength is vastly smaller than quantum theories predict, a discrepancy of 120 orders of magnitude that represents the largest gap between theory and observation in the history of science. This cosmological constant problem suggests we're missing something fundamental about the nature of space, time, energy, or all three. The identity of dark matter remains equally elusive. While its gravitational effects shape cosmic structure at every scale, from galaxy rotation curves to the cosmic web, its fundamental nature continues to elude us. Sophisticated detectors, deep underground, have failed to detect the particles that might constitute dark matter. Space-based experiments have found hints of possible dark matter signals, but nothing conclusive. The possibility remains that dark matter might require a complete revision of our understanding of gravity itself. The matter-antimatter asymmetry of our universe poses another profound puzzle. Our theories suggest matter and antimatter should have been created in equal amounts during the Big Bang. Yet we live in a universe dominated by matter. While various mechanisms have been proposed to explain this asymmetry, none have been conclusively demonstrated. The solution might require new physics beyond our current understanding of particle interactions. The quantum nature of gravity remains perhaps the most challenging theoretical puzzle in physics, while quantum mechanics successfully describes the microscopic world, and general relativity explains gravity and cosmic structure. Combining these theories has proven extraordinarily difficult. String theory, loop quantum gravity, and other approaches offer potential solutions, but experimental verification remains elusive. The extreme conditions near the Big Bang make this more than a theoretical concern. Understanding quantum gravity is crucial for explaining how our universe began. The origin of cosmic inflation, if it occurred, remains mysterious. While inflation elegantly explains many observed features of our universe, the underlying physics driving this brief period of exponential expansion remains unclear. What triggered inflation? What caused it to end? How did the energy of inflation convert into the matter and radiation we observe today? These questions touch on fundamental issues in quantum field theory and gravitation. The apparent fine-tuning of physical constants raises deep questions about our universe's uniqueness. Many fundamental constants appear exquisitely calibrated to allow for the existence of complex structures, including life. Is this apparent fine-tuning an illusion, a necessity or evidence of a vast multiverse where our universe represents a rare life-supporting configuration? The nature of time itself remains controversial. While we experience time as flowing from past to future, our most fundamental physical theories treat past and future symmetrically. The origin of time's arrow, despite its obvious presence in our everyday experience, remains debated. This becomes particularly crucial near the Big Bang, where our normal conception of time breaks down completely. the ultimate fate of our universe remains uncertain. While current observations suggest an ever-accelerating expansion driven by dark energy, the nature of dark energy itself remains unknown. Could it change over time? Might it eventually reverse sign, leading to a big crunch? Could our universe be one cycle in an eternal sequence of expansions and contractions? The possibility of life elsewhere in the cosmos connects directly to our understanding of cosmic evolution. The same processes that created the elements necessary for life on Earth operated throughout the universe. As we discover thousands of planets orbiting other stars, the question of life's uniqueness becomes increasingly relevant to our cosmic perspective. Quantum entanglement, which Einstein called spooky action at a distance, might play a more fundamental role in cosmic structure than previously thought. Recent theoretical work suggests that space itself might emerge from quantum entanglement between fundamental bits of information. This connection between quantum information and space-time geometry could revolutionize our understanding of cosmic origins. The role of consciousness in quantum mechanics remains debated. While most physicists favor interpretations that don't require conscious observers, the measurement problem in quantum mechanics hasn't been definitively resolved. The relationship between consciousness, observation, and physical reality remains a frontier where physics meets philosophy. The possibility of other universes raises questions about the nature of scientific explanation itself. If our universe is one of many, how can we scientifically investigate realms that might be forever beyond our observational reach? This forces us to examine what we mean by scientific understanding and explanation. The nature of infinity in physics and cosmology poses deep conceptual challenges. While mathematical infinities appear in many of our theories, their physical interpretation remains problematic. Are singularities like the Big Bang real features of nature or artifacts of incomplete theories? Can the universe be truly infinite in extent? And if so, what does this mean for our understanding of causality and existence? The emergence of complexity from simple physical laws presents another mystery. How did the simple early universe, dominated by hydrogen and helium, evolve into the rich cosmic ecology we see today? While we understand many of the mechanisms involved, the general principles governing the emergence of complexity remain debated. The universality of physical laws poses philosophical questions. Why do the same physical laws appear to operate throughout the observable universe? Are these laws truly constant, or might they vary in ways we haven't yet detected? Could different regions of the multiverse operate under different physical laws? The relationship between mathematics and physical reality remains mysterious. Why does mathematics so effectively describe the physical world? Are mathematical structures discovered or invented? The deep, mathematical beauty of many physical theories suggests a profound connection between mathematical and physical reality that we don't fully understand. The limits of knowledge itself pose fundamental questions. Are there aspects of cosmic origins that are in principle unknowable? How can we distinguish between what is unknowable and what we simply haven't figured out yet? These questions force us to confront the boundaries of scientific investigation. Looking to the future, new technologies promise to push these boundaries further. Next-generation gravitational wave detectors might detect echoes from the early universe. 30-meter-class telescopes will peer deeper into cosmic history. Advanced particle accelerators could probe new realms of high-energy physics. Quantum computers might simulate aspects of cosmic evolution beyond the reach of classical computation. The search for a theory of everything continues, seeking a unified understanding of all physical forces and matter. Whether such a theory exists and whether human minds could comprehend it, if it does, remains uncertain. Yet the pursuit of this ultimate explanation drives theoretical physics forward. As we push the boundaries of knowledge, new mysteries inevitably emerge. Each answer reveals new questions. Each discovery opens new frontiers. This endless cycle of discovery and wonder defines not just cosmology, but the human scientific endeavor itself. Our cosmic origin story, while incomplete, represents one of humanity's greatest intellectual achievements. From the quantum fluctuations of the earliest moments to the complex structures we see today, we've pieced together a remarkable narrative supported by multiple lines of evidence. Yet perhaps the greatest wonder is that we, products of this cosmic evolution, can comprehend it at all. We are the universe becoming aware of itself, using the very laws that shaped cosmic evolution to understand our own origins. As we continue to probe these deepest mysteries, we extend not just our knowledge, but our very capacity to know. The story of cosmic origins thus becomes intimately connected with humanity's own story, our eternal quest to understand our place in the vast cosmic drama. The journey continues. Each generation builds upon the discoveries of the past, pushing further into the unknown. As we face these cosmic mysteries, we are reminded that the universe is not only stranger than we imagine, but stranger than we can imagine. Yet we persist in our quest to understand, driven by that uniquely human blend of rationality and wonder that has carried us from our first questions about the night sky to our modern understanding of cosmic origins.